Hello everyone and welcome to today's video. In this video we'll be looking at hashing. In particular we'll be looking at how it's linked to crypto. Obviously hashing can be used for various other stuff, but that's what we're interested in this series of video, right? So let's get started. Right, so hashing, also known as hash functions, message digest, one-way transformation, etc. It serves one purpose. Given an arbitrary size input, we are going to generate a fixed sized output. Okay. It has typically been generating 128 bits or 160 bits, but obviously that is not the constraint here. We do have other hashing algorithms that generate various other sizes. For instance, MD5 generates 128-bit outputs, but now that has been intensely studied such that a lot of attacks can guess what the original input may have been given the MD5 hash output, because 128 bits are a lot of different attack techniques combined, including like rainbow tables, etc. Allows us to guess what the hash may have been. We also have stronger hashing algorithm. I guess it's not really stronger, but rather it provides more larger size hash output, such that trying to reverse that is much more difficult. We have much less collisions and so forth. So SHA-2 is like outputting 256, even up to 512 bits of output data. Okay. So use of hashing in terms of generating a digital signature is quite straightforward. For instance, we have message M. This can be of arbitrary size. We put it into a hash function H such that it's H of M, so M is whatever. And then what we do is we sign that hash output using our private key, for instance, using the RSA private key. Okay. Then we can send the signature and the message M together for the receiving party to confirm that the message has not been altered. Okay, so this way we can make sure that the receiver can check whether the sent message is legitimate or not. Okay, so from the receiving end, received message M, and typically sending and receiving message should be encrypted using one of the encryption standards as before, but that's the separate channel. Once you receive it, the hash function is known to all parties, so this hash function is public. So we chuck it into the hash function. We should be able to generate the same hash output. And then we use the signature. Signature has been signed by the private key. So we grab the sender's public key and unsign it, right, to receive the hash function and check whether that's the same hash that we received using the message or not. Okay, so we can check the M and the signature to validate whether the message is valid. So the application of hashing is not just for digital signatures, but we can also use it for password hashing. So you can think that your password gets hashed and stored in the database. At first, it seemed pretty secure, but nowadays, because hash functions are being cracked, which means people use different techniques to reverse back to retrieve the original message, it's not necessarily very strong to only store your raw password. So instead, what you have to do is add what we call a salt. Okay, so we have a password, and then we add a salt. Then it becomes a hash of password plus salt. This way, it resists a lot of dictionary attacks that trying to guess what the original text may have been. Because if you think about your password, a lot of people will be using something that is more familiar to them. So we don't necessarily use a random alphabet letters, uppercase, lowercase, special characters. Maybe some of you do, but majority others will use maybe words that are familiar to them, right? So this way, we can get rid of that staticness and add that randomness to our password after when it gets hashed. Okay, so think like the counter mode. where you have not just a counter, but you also have a nonce, right? Nonce is a randomly generated string of bytes, and salt is serving the similar role here. Okay, but other than password hashing, we also have message integrity using message authentication code. So this is your MAC. Basically, we have an agreed secret key K, and then we can compute h of m concatenated by key, and then send with m. Because we assume that the hash value is not traceable backwards to the original input, it can be put into a hash function. The key can be put into a hash function based on that assumption. But of course, if your hash function is weak, obviously your key will be in dire danger. Okay. This way, however, it does not require any encryption algorithm, so you can just send to. This is only for authentication code. This only authenticates the message rather than making sure the message is secure. So message can be sent in other way. Okay, but other than that, it can be also used for file integrity checks, like forensics. When you download like software, for instance, it gives you like a MD5 hashtags, SHA-1 or SHA-2 hashtags, right? So what you do is you download software, the binary chucking into the hash function, it should create the same hashtag. Otherwise, not hashtags, hash values. Otherwise, we know that somewhere along the pipeline, when you receive the software, somebody may have altered that binary, and it might do something else. We'll have a look more about that. Actually, we do an example using mobile apps in Lab 10, so you can stay tuned for that. But it can be also used for generating random numbers and so forth. So application of hashing is large, but in this particular one, we're just going to be looking at how to create these two signatures. Okay, so let's look at an example of using RSAs, because RSA we covered it in a couple of videos back, so we can use that. So let us use RSA to sign the message. This will follow quite closely with the example steps that we have seen before. So Alice first gets the hash of the message, h of m, then sign using her private key d such that the signed message s is h of n, the hash to the power of d mod n. So if you remember the RSA operations, this you can apply to decrypting an encrypted message to retrieve the plain text, but instead we putting in the hashed message in there instead. Then Alice sends the encrypted message, so that means you can encrypt the message and also send this signature together. Okay, so from outside, if you want the plain text, you need to crack that encryption mechanism, and if you want to alter the sign, you need to crack the RSA system as well. Okay. The receiver Bob can check the authenticity of the message by comparing the message m and s to the power of e mod n. So that means Bob can decrypt the message, the encrypted one, right? And then put it into the hash function to generate the hash of the message. And also Bob can undo the signature by using Alice's public key, okay? And then check, after you undo it, you get the hash of the message. So you can check whether those are the same or not, okay? So let's have a look at actual example of doing this, okay? So let's say the message m is 6, 14, and 11. And by using Bob's credentials, the C becomes 51, 49, and 11. But to encrypt this, you can use any other encryption standard. Okay, so the encryption stuff is separate to us. So if you want to know what are the different ways of doing this, you should look at either the RSA video or some of the symmetric cipher videos. So now the encrypted message C can be sent to Bob, and Bob should be able to decrypt it to receive the original message. Okay, so that's the message part. But with the signature part, what Alice will do now is run the message into the hash function. And this hash function is just using a very simple one, but in practice, we have much complicated process. But here, let's just say that this simple hash function is the summation of 3 times the message plus 1 mod 11. So if you calculate that, so 6 times 3, 18 plus 1 is 19, and then plus 14 times 3 plus 1 is 43, etc. Okay, so if you add them all up, you will end up generating value 8. So 8 is our hash value for the message 6, 14, and 11. So now we have the hash value, we're going to sign it. Sign it by using your private key and then raise it to the power. So Alice's private key is 27 mod 55. So we compute 8 to the power 27 mod 55. So if you scribble it out, work it out, you'll get value 2. Okay, so our signature is now 2. Okay, so what Alice sends is now the encrypted message ciphertext C and S, which is 2. Okay, so inside the bracket there, right over here. Okay, so now Bob receives this. So the message is encrypted, so the Eve cannot see the plain text. And sign 2 is also visible. Eve can use the Alice's public key to retrieve the hash of the message, but the assumption is the hash algorithm is strong enough that you cannot retrieve, you cannot go back to the plain text. So for given 8, how would you generate 6, 14, and 11, correct? There's a lot of ways to do that. So in a more complex hash algorithms, this is much more difficult. Okay, so in that way, for Eve, we cannot really alter the ciphertext. It's very easy to figure out if something is changed. Same with the signature. If I change the signature, then later the hash value is going to be different. Okay, so in that way, whatever we're sending now is quite secure. So Bob just need to be able to check whether the message is legitimate or not, right? So Bob can decrypt the message as with any other encryption standards, and then calculate the hash of the message. So that's the one step. And then the other step is we need to decrypt the sign of Alice using Alice's public key. So what we need to do is 2 to the power of Alice's public key, which is 3, mod 55. This gives us 8. So you can instantly see that this value 8 matches the hash value that Alice calculated originally up there. Okay, so since those two values are the same, Bob knows that this the ciphertext length is correct. Therefore, the plain text retrieved from it is also correct and has not been altered in the way. Okay, whether the sign gets altered or the plain text gets altered, then it's not going to match one way or the other. So you can try to change the message or the hash value to see whether you end up with the same hash value at the end or not. Okay, so that's pretty much it. Using simple example of RSA for showing the sign, which involves hashing. So hopefully you understood some mechanisms of hashing and its good usage. Otherwise, I will see you in the next video. Bye.